as it is, FDP is predominantly on AI and ML, and I've seen most of the speakers are going to touch upon on data science, AI, ML, and things. My talk is actually going to be like how AI can actually be used in the current real-time system. So real-time meaning, like currently real-time meaning, we are talking about an IoT-based system, how AI actually can be used. So that's what I'm going to talk. So before we go into those kinds of things, like how it is being, I'll give some rudimentary basics about what AI is, what IoT is, some ML and things, because later on there are people who are going to talk in depth into deep learning and things. So I'm not going to go much into the mathematical, a little bit touch upon those things, and then show some of the case studies, the work done under my supervision, how it can be done. So that can be taken away by the people sitting here to carry out their research or projects or whatsoever. Okay. So because of bandwidth, I'll just switch off the video later on. So it will be easier for everyone to follow it up actually. So let me first share my screen. If there is any connectivity disconnection, please just WhatsApp me or something, because it happens at times actually here. Okay. So, so that's going to be the title of my talk today: applications of AI in an IoT-based system. So that's why I said, like, in real-time situations, like how artificial intelligence is actually going to play its part in IoT-based system. So the end of my talk is actually going to go like this. What exactly is IoT? Most of people nowadays know what IoT is, but some might be still not aware that much. So what exactly is IoT? What are the technologies in IoT? Then a new kind of a technology which is being talked heavily nowadays is the edge and the fog computing. And then we'll get into artificial intelligence, some of the basic rudimentary things regarding machine learning and deep learning. Then agent technologies, which are also what is called a subset of AI. And then the integration of AI with IoT and edge, and some of the case studies and some future directions. So Internet of Things, if we talk about, the generations has actually seen lots of actually changes in the field of technology, in IT, you can say. So initially we started with what is called like mainframe computers, then we saw like desktop, then we saw what is called like networking, wherein like people can actually connect and try to access the data from a database servers and things. Then with the advent of wireless technology, sitting at any point of the world, actually you can browse, you can get the information. And then with the advent of mobile communications like 3G, 4G, now there is no boundary that you have to have internet, because internet is always available at your hand actually. Because previously it used to be like we have to run to the internet center or you need network connection at the home. But now mobile technology has made things so easy that everything is happening at your doorstep or at your fingertips today. Even this COVID thing, if you look at it, because of these mobile handsets and things, we are able to do lots of things actually. From education to many things, it's actually possible, right? But Internet of Things actually goes much more beyond that. Rather than just connecting to the internet of things, it's about like not just mobile handsets or things, it's about like connecting to things. The things we are referring is just not the sensors, it is referring to objects. That is, it can be from your home appliances, like your microwave, like your refrigerator, then your car, your vehicles, your watches. Everything are actually going to be interconnected. They are going to talk among themselves. There is no need of any human who is actually going to tell this is what you have to do. For example, let's say you switch on a geyser, you forget it. You don't have to be remember or anything. The device is going to talk among themselves, and automatically any kind of a control action like switching off or thing can happen. Most of the time we actually forget to switch on or switch off the motor, right? So these things also would actually come in the world of IoT, where the objects can talk, and based on that actually like it can be switched off once it reaches a particular threshold levels or things like that. So it's about like talking among themselves and connecting to the internet. So these devices which we are talking about, it can be millions and billions of things that are all going to be connected to the internet. So Kevin Ashton, the father of IoT, says that turns the world into actually the data that could be used for macro decisions on resource utilization. So it's nothing but like all the physical gadgets, starting from your car key to your vehicles, your appliances like microwave, your air conditioning, geyser, refrigerator, to anything is actually going to be interconnected. They're going to talk among themselves and get connected to the internet for further analysis and so forth. So this interconnection is actually opening the doors for lots of straightforward coordination and things like that. And what it ultimately gives us is like improves what is called the proficiency changes, some commercial advantages, societal application. So a survey in 2017 states that 8.4 billion IoT gadgets. Okay, just not 80 devices, 8.4 billion. So you can think that number of objects which are actually going to be connected to the IoT, because the country is also talking about digital India and smart city. For that to become a reality, IoT is the solution that we have in the hand. So much of devices and different people, the population and thing in the world are actually going to be connected to this internet. And by 2020, they are saying like 30 billion gadgets are going to be interconnected. And the world's estimation is like IoT is anticipated to have $7.1 trillion. So the applications of IoT actually span a lot, starting from your smart grid, smart water management, agriculture, healthcare, transportation, even like surveillance, lots and lots of things, and education. Many places IoT has tremendous applications that you can look for. So what are the backbones or what are the underlying features of a IoT? If you look at it, first thing is the communication. There are lots of communication technologies we have seen. So IoT is actually based on some of the standard communication technologies, which is just not Ethernet or Wi-Fi. It actually relies on lots of communication technologies because each object actually operates on different communication standards. So things like 4G, then 802.15.4, because the wireless personal area network, Zigbee, RFID, and for IoT, predominantly like our home automation and things, they brought things like Z-Wave, Thread, Sigfox, and things like that. And also, because all these things like Zigbee and things. Okay, you want me to use a headphone? Okay. Let me see. For me, like without headphone, would it matter? 1 minute, I'll just put the headphones on.
It's clear only, sir.
Okay. Okay, is it audible now?
Yes, sir.
Okay, all right, okay, thank you. All right. Because all these devices are not IP based, they all operate like on like Zigbee and 802.15.4. Because these devices have to connect to internet. For internet, if you mean IP address is the only way that devices can be recognized. So they have brought what is called 6LoWPAN, which is nothing but IPv6 over 802.15.4. But the same 128 bits cannot be adjusted. So they have compressed it, like putting what is called an adaptation layer over there. And the top, we have what is called the UDP communication. So 6LoWPAN is actually being brought. That's the first thing. Then the backbone network is actually going to rely on the standard backbone networks like the TCP, Transmission Control Protocol, and UDP. Then hardware, if you look at it, these hardware devices that we have been talking about, like embedded systems and things, they were actually operating for quite some time. But today's hardware devices are coming with what is called like system on chip, meaning like they are actually embedded with wireless capabilities. Okay, so such kind of things are actually being brought, because the reason being nowadays embedded system is not a separate thing; it has become a part of IoT. So these things has to be embedded with the wireless capabilities that will allow you to communicate to the IoT system, that is the internet. So prototyping chips like Arduinos and things are Raspberry are making it conceivable to make the client's own IoT devices. Right. So yeah, that's a third thing. And the fourth thing here is protocols. So in like wire or wireless, there are some standard protocols we used to use because IoT is actually dependent on various communication technology because each object is actually going to use their own communication standard like ZigBee, RFID, then 802.15.4, Bluetooth low energy, Z-Wave and thing. So they actually came up with what is called an IoT application layer protocol. You might wonder why application layer. The reason because IoT is not dependent on any type of communication technology. Because if you're going to depend on that, then you have to keep on actually changing the protocol for each and every communication standard. So they actually are not bothered what is the communication technology happening beneath that. They're only worried about how the data is actually going to be sent to the internet. So they actually rely on what is called an IoT application layer protocol like MQTT, CoAP, AMQP, and DDS. So they are not going to look whether it is a ZigBee or Bluetooth or anything because these protocols can support any kind of communication technology and they are only bothered about the application. The reason being, IoT is predominantly focused for application scenarios. So that's why they come with so much of application layer protocol, which runs, of course, on top of TCP or the UDP thing. Then the software. So different types of operating system for these kind of IoT has actually been brought. Like our IoT OS is actually the thing for such kinds of gadgets actually. Now, the basic thing actually for you to connect to the objects is basically the cloud and the machine learning because the data that you gather, which I said, so many gadgets are going to be connected and these data are actually coming. You need to store somewhere, right? So that storage it cannot happen in database because the cloud, when they actually initially designed, it was predominantly to ease out the storage capacity of what a normal database server or thing will have. But they never focused that IoT such thing is actually going to come and they are actually going to connect to the cloud where so much of voluminous data are actually going to come and it has to be stored for analysis. So that's why the world of big data analytics also was born out of the cloud computing in order to manage those kind of data. Then is the analysis. So the data that you gather and you actually manage it, it needs to be analyzed very intelligently. So you need to make some decision. Take for example, you are getting lots of healthcare data regarding the cancerous images or thing. You need to make an analysis like whether it is a cancerous cell or not. So for that, you need to bring in what is called AI. That is the machine learning, right? Like deep learning. So that would actually can do what is called the analysis of data and make a predictive classification or decision or whatever you're working on to give the intelligent decision for making some decision on that particular object function. So Google, Microsoft, Nvidia, IBM, they're all introducing what is called small scale embedded device because when we talk about IoT thing, everything are getting interconnected. They're also working on optimizing this machine learning onto the embedded devices also. I'll tell you why that is important when we come to the edge computing actually. So that's where we're going to understand like how its usefulness are actually. Because operating the such kinds of large machine learning on cloud is not a problem. When you're going to actually have intelligence on these embedded devices, you need to optimize on this machine learning in order to suit those kind of embedded devices because they don't have such big processing power or memory like what a cloud actually possesses. So just a run through about the different IoT is one is CoAP, Constraint Oriented Application Protocol, which actually is nothing but a compressed version of HTTP, we can say, runs over UDP. Then is MQTT, which follows what is called publish subscribe method, not like a client server method. So what exactly happens is when you want to actually get your data, you actually subscribe for it. So the devices would actually publish the data. So from whichever data you want to need it, let's say I want data from a temperature sensor or humidity sensor, I will only publish for that. Okay, so there will be many sensors. So how they have designed this protocol is there will be millions of sensors out there. They're going to generate the data, but I will not need the data from everything. So what will happen is the cloud or the IoT system are actually going to subscribe to that particular object. So the ones that you subscribe only those data will actually be published for you. So that is the publish subscribe method which MQTT actually follows. And XMPP is actually again another one that was for instant messaging. Then AMQP is for advanced message queuing protocol. That's actually for banking. They actually developed for transactional message server. and then they have what is called the data distribution service, that is for directly use on the sensor data. So just a quick comparison, if you look at it, like it actually runs over UDP, the co-op actually, it follows a typical request response, and the security level they use is GTLS because it's an UDP based. Then MQTT follows publish subscribe, which runs over TCP. It has what is called a broker based architecture here. Then was XMPP. Again, it has what is called a request response only and based on sensor data, where it actually follows what is called device to consumer and consumer to consumer. And AMQP also runs on TCP. DDS actually runs on both UDP and TCP. So all these things actually were developed in the days, not with the focus of IoT. They were all focused on the thing of based on cloud computing. That is the major challenge of this protocol. So these protocols were not devised actually with what is called the IoT or anything interface. They all were devised in such a way that these sensor data can transfer the data to the cloud. That's all. So with relevance to IoT or anything, none of these protocols were actually imagined or they actually devised it. So communication protocol, if you look at it, as I said, there are many objects in the world today, and every objects are going to be connected to the internet. You have various communication standards these devices are going to operate, starting from BLE, like BLE 4 is there, BLE 5 also has come. Then you have ZigBee, which has a standard operating at 10 to 100 meters. Then there is something called Z-Wave. It's like Z-Wave, Thread, and Sigfox were all designed with actually IoT in the mind. Then 6LoWPAN, as I said, is nothing but compressed IPv6 on the top of 802.15.4. Then mobile communication standard like 3G, 4G, and now we're talking about even like 5G, and even 6G is also there, which they are predicting like 2030 with ultra low latency. 5G itself is actually designed for IoT only, but they're talking about 6G also. Then new LoRaWAN, that is actually for wide area network communication. The reason is like for LoRaWAN, like if you want to actually capture the sensor data all the way from which is a kilometers away, LoRaWAN is a good one. But the only challenge with LoRaWAN is actually the speed. That is like the bits per second is little bit lesser as compared to 6LoWPAN and other devices. That is the only thing. But the range is actually, it spans like kilometers actually. So if you want to remotely monitor an agricultural field or things like that, obviously you can go for a LoRaWAN kind of a devices option. So the practical difficulties you have if you want to implement an IoT system is, first thing, the complete infrastructure has to be changed. Then, as I said, these IoT are nothing but an advanced version of sensors only they say. But it's not exact because not only sensors, you have different objects which are going to be wirelessly enabled. Then these cloud motors that we are talking today were not focused with actually IoT in the mind. They never thought about it because cloud was only designed for actually giving more storage space for virtualization and things like that. But they never focused that such a billion devices are going to be connected to the internet, and we have to do like huge level of analysis. So like billions of devices getting connected, that means you're going to generate like 2 exabytes of data every day. Think about a situation where I need to monitor the power line, or I need to monitor the power being distributed in a particular locality. So on a continuous basis, if I'm going to monitor and doing the analysis, this data has to be monitored and they have to be sent to the internet on a daily basis without any stop. So that will actually result in the amount of bandwidth that you are actually going to consume in sending the data. Because the reason is you are not the only one who are going to send it. Like this, there will be lots of data that is actually going to be used, where the bandwidth is actually going to be used to be sent to the internet, to the cloud. So bandwidth is a very big constraint which IoT actually has, particularly when the data is actually going to be sent over the internet to the cloud for big level analysis actually. Now, many of the devices we use today in the industries, like industrial controllers and things, they are not IP based. They have their own standards. So if you want to actually communicate the data from those industries to the internet, to the cloud, you need IP address. So they all have to be transformed into what is called an IP based system. Like we are talking about industry 4.0, 5.0 and things. So that most of them, they don't actually go with IP based system. They are all having their own industrial controllers and their own industrial specific. For example, electrical like transformers, they have what is called IEDs. they have a standard called IEC 68150. So they are recently started to actually adapt to IEEE standard to make it IP based. So only if you make those devices IP based, these devices can be connected to the internet, because the internet understands only one type of addressing, which is IP addressing one, nothing other than that, right? So it all has to be transformed into IP based addressing actually. So now all these things together, the major challenge we see here is the latency and the bandwidth is a very big issue actually. So if the latency is actually going to be high, that is surely going to be, when you're going to connect such a billion devices actually to the cloud, obviously you will be having lots of bandwidth constraint and there will be lots of latency. Now, edge or fog actually comes as a solution to that. Edge and fog computing was introduced by Cisco way back in 2014. Why they actually introduced it is a question. Now, let's take a real-time situation. Let us take, for example, you are monitoring, let's say, an agricultural field, or you're monitoring, let us say, a power distribution, in a particular area. Particularly, let's say, a transformer's health or a power line communication. Now, the data that you are actually monitoring, and that you are going to monitor for an entire city. So the data that you are actually monitoring is actually going to be sent to the cloud. Okay, the data that you're actually going to monitor is actually be sent to the cloud. So on a regular basis, the data from each and every geographical location and the locality is actually going to be sent to the cloud. And the analysis is actually going to be done in terms of like how the power is delivered, how the health of the transformer is, how is the oil level, oil temperature, and those kind of factors, power factors, voltage, what is the level of voltage, supply current, all kind of things. Now, each time you actually keep on sending the data, an analysis is happening at the cloud level, right? Now, when you're doing the analysis, obviously you'll see the trend of the data and also see like if any kind of surge or anything, you have to take some action. So that response, when it's actually going to come all the way from the cloud to the actuators down, it has to reach in time, because the bandwidth is actually very less. You have a really constrained bandwidth because you can't actually try to give as much as bandwidth as number of devices connected. It's highly impossible, because like here, you might be having many devices for other applications be connected, probably for traffic, health, water, many things actually. So the bandwidth is actually going to be very less from it. So when the response that you do the analysis is not going to reach in time, whatever action you take, it actually goes as completely waste. It has no meaning at all, right? So that is the major problem that actually motivated the Cisco engineers to come up with a technology called a fog computing. So what fog computing predominantly focuses on is like minimizing the latency and actually working on reducing the workload of the cloud. So that is the major thing, because milliseconds actually matter, particularly when you're trying to prevent a manufacturing line shutdown. So simple manufacturing line shutdown, if you do that, will result in lots of production loss and things. Edge and fog computing actually gives a solution wherein you can process your data closer to the devices. So next question that will happen in your mind is, so does it mean that cloud is not at all needed? No, we don't say that. Cloud is still needed. Cloud is still going to be there, because you can't give the same amount of processing power as the memory what a cloud gives, the edge of fog cannot give. But we are only providing a solution where the devices will be situated closer with some good amount of processing, wherein the data can be done locally. Locally, you can do any kind of analysis and a quick control action can be taken. So the latency and the cloud's workload will actually be reduced. That is the first thing. Then the second thing is conserving the network bandwidth, because as we said, when you have millions of data getting connected and the data is actually keep on going to and fro every day, obviously the bandwidth would not be enough. Rather, if you are actually going to capture the data closer to the devices and process that and take some predictive action by applying some machine learning algorithms or deep learning and things, that will be even better, because the bandwidth usage will be optimized actually. That is the second solution what edge and fog computing gives you. Then reliability of the operation. IoT data is increasingly used for lots of decisions, right? For example, like diagnosing a particular disease, then actually giving some control action based on the health of the transformer, or giving some control action to the industries, let's say chemical industry or oil refinery industry. So the reliability of the data has to be really looked at, because that ultimately affects the citizens as well as the infrastructure. Take a simple example that we want to intelligently control the traffic congestion in our city. So whatever control action you give and thing is actually going to affect the citizens. So the reliability of the system has to be really looked into. And the fourth thing is collecting the data securely across a wide geographical area, because security is always a concern, particularly when you talk about a wireless domain. And with the IoT thing, it has more serious issues actually. So securing this data is also very important, which is taken care of the edge and fog computing when it's actually distributed over a large square kilometer. And move the data to the best place for processing for quick decision taking. So that's exactly what the problem that IoT is actually facing in terms of the latency and the bandwidth and thing. The edge of fog computing actually is where you do the processing locally near the devices. So decisions actually, whatever you take, can be acted very quickly rather than the time it is actually going to take to get the decision all the way from the cloud, because you don't know where the cloud is located. It could be in the US, it could be in Singapore, it could be Europe, it could be anywhere. So that bandwidth is also very less, and you cannot actually give such an amount of bandwidth for the ever increasing number of devices. So what is this edge and fog? There's always a misnomer, like is it edge computing or is it a fog computing? Edge computing is nothing but called the edge, meaning like near the devices. You have what is called a computing technology. That could be anything. That could be a Rightly processor, that could be a Raspberry Pi, that could be a BeagleBone, or that could be even a mobile device. As long as it has some good amount of processing power to process the data, capture it from the IoT device, and that is what is called as an edge. And wherein after that, it should have the wireless connectivity to transmit the data all the way to the remote cloud. Cloud computing framework for handling such kind of a data. That is what is called as an edge computing or edge processing, wherein we are going to keep that edge very close to the devices actually. So the data can be captured locally, and it will actually perform some filtering, whichever the data are relevant, which is necessary for the processing, and apply the appropriate decision or the AI mechanism to do it and give the control action for performing it. The rest of the data will be sent to the cloud for macro level processing, like big data analysis and things can be done. Then what is this fog? Fog is nothing but a standard which is coined by Cisco for these edge computing devices. They say the fog computing, where the processing is happening at the edge level. Like what we say, like 802.3, it's a standard coined by IEEE. 802.11, standard coined by IEEE. Similarly, the processing that is happening at the edge, a standard has been coined by Cisco called a fog computing. Okay, so that is the thing which encourages the task of like filtering the data, stockpiling, system administration, the benefits from end-to-end devices, security, everything is actually offloading, resource management. These things are actually architecturally they have specified that this is what is a fog computing standard where processing happens at the edge. So there's no much difference actually. It's nothing but processing happening at the edge for reducing the latency and the cloud workload and giving some quick control action. So a typical diagram, like when they initially introduced in 2014, right, like they actually said, like this is how fog computing should be. So you have what is called the devices, which is at the bottommost layer, which can refer to anything, your objects, your IoT devices. It could be your smart energy meter, it could be your sensors, it could be a smart watch, it could be anything. And then you have an edge device in between, that is your fog computing, which is actually going to process the data that is actually going to be captured and perform the real-time analysis for quick decision. And then you have a cloud, which is actually going to store all the data for big data level processing, which is going to be managed by the data center. This is exactly what they actually focused on fog computing is. Further to that, there has been some work that was actually done by a lot of researchers in the area of fog and edge computing to come up with something called a software-defined multi-type fog computation model. The reason for bringing this one is because, see, when you're actually going to come up with an architecture for this one, you cannot actually rely on what are the standards that is happening with the hardware and thing. So if you're actually going to actually bring in what is called hardware dependency, it actually becomes very much harder for you to deploy any kind of real-time applications in the edge level devices. Because if you're going to say like if the data that is actually coming is following this kind of a communication standard, like 802.11, 802.15.4 or Zigbee or thing, and accordingly you're going to start developing the software, then it becomes very much hardware dependent. So it becomes very hard. So as I said, these are actually going to follow a kind of communication protocol called publish subscribe, MQTT. So those protocols were actually focused with cloud computing model in the mind, because IoT or edge of work were not the cup of tea at that time actually. So that protocol was actually modified to actually accommodate this edge of work computing, wherein we introduced what is called a software-defined remote broker at what is called the, if you look at the diagram here, we have what is called the layer 2, that is where the edge of fog level is, and the layer 3 is my cloud. So previously they never had any of this edge of fog, that the devices used to communicate directly to the cloud. So because to reduce the latency and thing, we are bringing in the edge of fog computing level has been demarcated with an architecture here, wherein we introduce what is called a broker. Now this broker we are talking about is not going to be dependent on any hardware. It's a software-defined broker. You can actually develop the broker in any language of your choice. It can be Python, it can be Java, it can be any language. So the underlying hardware technologies or communication is not bothered for it. It can be anything. And this broker's main job is when they actually publish the data, it will subscribe for it, and those data will be actually captured by the broker. Then once the data is actually captured by the broker, where all the filtering and those kind of a thing are done, and then we have something called the analysis. When we talk about analysis, sometimes the data could be something, it could be critical, where a quick decision has to be taken in order to perform the control action. For example, we're actually monitoring the health of a transformer or the health of a pipe or things like that. Let's say like, it is in a critical situation, you need a quick decision to be taken. That is done at what is called the tier 3. Where based on the data, it will look to see like it's a critical or non-critical, and a quick control action will be taken. Then is the edge computing node. There what happens is the data is not critical. So that is where your machine learning and AI part actually comes into play about the broker once the data is captured. Like how the data is actually going to be analyzed based on the criticality and the non-criticality. If it's non-criticality, you're actually going to study what is called the trend of the data, accordingly give a prediction. Finally is the intermediate node, where it looks for the data duplication. So this is exactly a software defined one, wherein the underlying communication hardware you're not bothered about. Everything is purely software defined, and you can actually deploy your application irrespective of whatever kind of a situation you want. And then actually as we propose, and it was proven theoretically as well as practically, that with this kind of a model, you have very less latency compared to the traditional IoT model actually in terms of transmission, service, and processing latency. You can actually Google to get this paper actually, and you will get more details on this. Now, okay, now that I said lots about IoT and things, what's happening, now let's get into the main thing, which is the artificial intelligence. Intelligence is something always any human being will possess. He could be the most intelligent person in the world, the smartest person, or he could have some average intelligence. But what exactly is this intelligence at the end of the day? Intelligence is something like when you see something, you have some intelligence with you, where you can actually interpret this is what it is actually, and accordingly perform the activity, right? That is what a human being actually possesses an intelligence. Or as we say, like he's a dumb guy. That's exactly what is the word we actually say. Now, what is this artificial intelligence? A machine we talk about, let it be a sensor, let it be an actuator, let it be your Arduino, let it be a Raspberry Pi, let it be a mobile, whatever it is. It is nothing but a mere box. That's all. It does not have any kind of an intelligence. This intelligence has to be brought inside actually these devices by the human being. How will you give that intelligence? It's not a thing that it can actually hear, it cannot see, it can't do anything. It's not a human being. So that intelligence has to be given by what is called a human by means of certain process. For example, like writing the software programs, algorithms and things. where the machine is actually given the intelligence and accordingly it starts to behave. For example, you are having a temperature sensor. So when the temperature rises to that level, it will actually give an alarm saying that the temperature is shooting above the threshold. You might have heard about the smart watches where it actually measures your BP and things like that. What does it do? It actually keeps on giving you the BP level. When it is actually going above certain thing, there will be intelligence that will give you an alarming sign that it is reaching a threshold value thing. How does it do? Because it is doing based on the intelligence that is actually written inside the particular embedded or IoT devices. That is what is called artificial intelligence, meaning you are embedding the intelligence artificially into the system to do lots of things, starting from a simple regression to the advanced deep learning, where you can do things like classification, prediction, NLP, like Google Assistant. When you say something, it actually understands what you are saying and accordingly transforms into text and performs the job. When nowadays, when you do the Google search, when you type the thing, it automatically understands what you are looking for. You don't have to type the entire thing. These things are AI. These things are AI, which is actually being developed in the system that we are enjoying those kind of a thing. So AI has similar to IoT as how it has become a part of the human life now. AI has actually become a part of a human life. There is no such thing today that without AI we are actually living. You take for example anything, your YouTube, your Google search, or you're searching for your restaurants, hotels, whatever it is. Somewhere or the other, AI has actually become a part of the human life, similar to the IoT-based system. So AI, in a way, is actually going to make a characterization of replacing the human behavior. So why is AI important? Automation. As IoT has already come into this world, where it is actually interconnecting all the devices, and they're trying to give a level of automation, right? With sensors and devices connected to the internet and things. AI has to become a part of IoT, wherein such kinds of decisions or automation is possible only with this intelligence inside the IoT. So both actually goes hand in hand. It cannot be something like IoT can exist on its own, AI can exist. No, it is actually become a part of it. Both are actually a part of it. For the data generator, for you to make a quick decision and analysis, I think AI has to play a very, very prominent role there. Only then actually you can make an intelligent decision and perform the activity. That is one thing. It adds intelligence, of sure. Then adapts to progressive learning. So how does the system learn? Like, now this is how the pattern of data is, and this is what the kind of activity or this is kind of a decision I've taken. Does it actually learn just like that? No, it has to learn through progressive. That means that you're going to teach the system, this is how the pattern of data is, and this is how the data pattern looks like. This is how the trend of the data is. And accordingly, the system actually learns, and finally it gives you a decision. Like this is what it is. This is A, this is B, this is C, and things. So that is actually done by means of what is called a progressive learning. Now, for you to learn and actually understand all these things, the AI actually goes very, very minute, deeper into the data to understand the features and things like that. And when you actually think bringing such kind of a model, it tries to give a very, very incredible accuracy. Of course, these things actually varies from model to model, and you try to get the most out of the data. So that's how AI has become a part of the human life, and it has become very, very important. Just similar to the IoT, which I was talking about. Now, one of the subset of AI is what is called as machine learning. See, the precursor of machine learning, I always say, is data mining. Because if you just look into like data mining, most of the algorithms we are talking today, like clustering, classification, that has been applied. In the previous generation, actually, data mining was a part of database system, where actually you mine for the data and you try to do the classification, prediction, and things. But they never imagined that this kind of a thing is actually going to be such a boom in the world that it is actually going to be applied in every aspect of our life to predominantly do lots of automation and things. So machine learning is actually an extension of data mining only, I would say, because those data mining and things were also a part of database, then the cloud system where these kind of things were applied. But with the advent of IoT systems and things where you want to actually capture the data and give a quick analysis and things, so they brought it as what is called as a machine learning actually. So it's a branch of AI. That is one of the branch of AI actually. And what the great scientist Tom Mitchell, who is the pioneer, like Kevin Nash of IoT, says that it is nothing but a study of computer algorithms that you are making the program to automatically improve through experience. Very simple statement. That's all. It's nothing but a computer algorithm. He says that's all. Nothing else other than that. But you are making the system to actually improve it through the experience. How does that improvisation happen? That's happening because of the progressive learning that the system actually does by means of this algorithm that you have written. That is what is a machine learning, meaning the machine learns through experience. For that is what we're bringing the data set, we apply the different model, we actually train the system, and accordingly it is learning. That is why I say in AI, one of the things is progressive learning, and it learns through the experience, it tries to improve the accuracies and things like that. So machines will be trained similar like a human being to perform various activity. Classification. Let's say I have a bunch of mangoes and things. So I need to actually classify which one is, in our language, meaning like different types of mangoes, which is an Alfonso, which is the other one. That can be done. You can actually capture the image, and there are intelligent algorithms that can be applied that can actually classify, like which is Banganapalli, which is Alfonso. Yes, that can be done, right? Similarly, you want to do some kind of a prediction. So let's take, we take an X-ray image or something, and I want to actually make a prediction whether it is a cancerous, whether it is actually having any kind of a problem in the lungs actually. Okay. So let's say when we take a CT scan, we try to find out whether there's any kind of a malignancy thing. That is also possible. Then clustering. Things like I want to group it. Let's say I want to group the students based on, let us say, his marks or GPA. That is also actually possible. So machine learning actually relies from a very smaller data set to a very huge data set. That is, it can even work with 1,000, or you can even work with 100,000 or even more data sets actually, wherein you try to find a common pattern. That is why I said in the age of fog computing that it looks for the trend of the data. That is how the data trend is. Only then I can make some decisions actually. So the pattern of the data and everything is actually looked by what is called the machine learning. Only then it can actually come to a conclusion as how to make a decision actually. So in machine learning, there are two phases we say. One is called the training phase. The other one is called the testing phase. What is this training phase? Training phase is a phase wherein we actually look into the pattern of the data, and you actually use certain algorithms to teach the machine. This is how the pattern of the data is, and based on this pattern of data, I think this is what is the output. That is what you actually try to teach the machine. That's what we call it a supervised. We just come in the next level, supervised and unsupervised. So when you make the system to learn like that, by experience, it starts to accumulate the knowledge. That knowledge is actually accumulated by the system, and it now knows like if the pattern of data is like this, this is what the output is going to be. Then in the testing phase, you give completely a new kind of a data, because the model has already learned. It will try to predict maximum, the best accuracy with the best prediction possible actually. Okay, so that is what is a machine learning. So in a simple example I've given here is, as I said before, the X-ray pictures, where it tries to look for certain symptoms actually, or a CT scan. So based on the image data sets where the machine is trained, when you give a new kind of an image data set, it will be able to make a prediction whether the lungs has any kind of malignancy or not. Similar to what a radiologist or a doctor can actually say. So when you go to the classification of machine learning, as I said, there are three classifications. One is supervised. Supervised meaning you tell the machine if the pattern of data is like this, this is what the output is. That is why I say it will have what is called an output label that will tell whether it belongs to class A or class B or class C. That will be told. Accordingly, based on the algorithms you're going to apply, the machine would actually learn, and it will actually say that this, if the pattern is like this, it belongs to class A. If the pattern is like this, it belongs to class B. So like that, you actually train the machine. So when you give a new test data, obviously the machine will give a prediction with the best accuracy and reduced error. Now for this, obviously you need quite a large data sets, like a historical data sets is actually needed. Like for example, the X-ray images, and you need some good amount of data sets about the X-ray images. Only then you can make the machine to understand like how it has to diagnose between cancerous and a non-cancerous image. Then is unsupervised. Unsupervised is something where you don't know what the output is going to be. So these are predominantly used for certain things like pattern detection and descriptive modeling, where they try to apply certain clustering algorithm in order to group it actually. Because here we don't know what the output is actually. So that is what is unsupervised. That is an unlabeled data. Then you have what is called a reinforcement learning. Now, reinforcement learning works not on the principle of data sets, but it actually works on the basis of what is called the interaction action. So reinforcement learning actually works on the principle of what is called an interaction. That is an agent interacting with an environment. So environment could be anything. The environment could be like a medical field, could be an electrical field, it could be water, it could be something agricultural field. So based on the interaction and thing, it actually learns. This is how actually it will interact. This is how the output should be. And based on that, you actually try to maximize the reward or minimize the risk action. So it actually goes through a sufficient iteration where the agent will actually learn and accordingly give that decision. So it does not have any kind of a prehistoric data sets or anything on which the computer can actually learn. So that's a diagrammatic explanation of supervised. So if you look at here, you have what is called the duck. So this one actually will have a label like if the image looks like this, it is a duck. If the image looks like this, it is not a duck. So when you give a new data set here, so the model which has been trained will actually give an output like this is a duck. Unsupervised is something like it has all the images, but it does not have any label like which is a duck, which is not a duck. So you try to group it based on certain features actually, probably based on the color, based on certain feathers, something like this. Accordingly, you actually group it to get the output. And then this one is a reinforcement learning, wherein you can see the agent will keep on interacting with the environment. Based on the iteration and thing, we actually try to maximize the reward and accordingly perform the action. This is also a very fast coming field in machine learning called reinforcement learning. So some of the rudimentary basics that is actually needed for anyone to delve into machine learning are, one is overfitting and underfitting. There is something called the bias and the variance, and some of the hyperparameters. Then things like the metrics that you have to use in order to validate the machine learning. Some basic things actually. Overfitting. So there are two things actually we look into the machine learning. One is whether the model is overfitting or the model is underfitting. See, whenever you get a data set, you cannot blindfoldly apply a machine learning algorithm. The first stage we actually do here is what is called the data cleaning and the data pre-processing, where we look into what is called explorating the data. Okay, we do what is called the data exploration to see how well the data is balanced, where there is an equal distribution of the data. Where if you have, let's say, class A and class B, let's say it's a supervised learning, we make sure that there is an equal distribution of the data among the two classes. So at least like if it's not like 50-50, at least it should be some 30-40 combination or something, where it is at least to some extent equally distributed, following a bell curve or something, or at least equal to a bell curve. It should not be something that most of the data are biased towards one class and very less data are there in one class, or too much of data is in one class and less data is there in the other class. In that case, they actually perform certain mechanisms like sampling techniques in order to increase the data and make the data well balanced, called the sampling techniques. Things like we have like oversampling, undersampling, smarting, and things like that. So they try to increase the sampling or reduce the sampling. They have some mechanism. Now, let us say that you have looked into all this thing and you're not looked into it accordingly applying a machine learning. So what happens here is, if the data set is not properly cleaned, cleaning meaning not just cleaning, it's meaning like you look for some missing values. You look to see like whether the data is completely properly processed. if the data set is not cleaned properly, the missing values are not taken into consideration, none of the thing is done. So what the machine learning will actually do is, it will try to actually take into account along with the data, the noise meaning the dirtiness in the data. Okay, the noise is something, there is unwanted information in the data and learns from itself. So some of the unwanted information also would be learned by the model. That ultimately will have a negative impact in terms of a prediction or a classification. So that's why data cleaning is the first stage that you actually do in the machine learning. Without that, you cannot proceed for applying the ML, because it will obviously result in what is called a wrong result. It will actually give you a prediction like you have 100% accuracy, which is practically not possible. So this kind of noise and dirtiness in data, if it is not removed or it is not properly handled, it will lead into what is called a fluctuation, leading to what is called an overfitting. Okay, an overfitting thing actually will come. Overfitting meaning, let's show it again. This is what is called as an overfitting, meaning when you actually train the model and thing, and then we're going to give a test data, what will happen is the entire data that you are given, the test data, will fit that model perfectly, 100%, without any kind of an outlier. Outlier is something like when the points lie outside the particular line. That means it's 100% perfect, which is practically not possible in this world. It's highly impossible. So this is what is called as overfitting data, wherein it has learned not only the data, but also the noise, which is actually causing the fluctuation or the dirtiness in the data, because the data was not handled properly, the balancing was not done, the cleaning was not done, and the model has actually learned and it has given this kind of a prediction actually. Okay, so certain algorithms actually are there which actually has a very much susceptibility of overfitting, which are like decision tree. So for that, they actually try to prune the tree actually that is learned in order to remove some of the detail that it has picked up actually. Okay, so in that case, actually, overfitting comes in, particularly in decision tree and random forest. There is quite a likely chance of actually having what is called overfitting, because it's a non-parametric model. So obviously, it tries to pick up overfitting problem. Underfitting is something you can just look into it and actually find out like, yes, it will lead into underfitting, wherein the data sample you have is too less to actually train. So if you have only like say 100 data sets and things, is very, very less that we can train. So what will happen is it will obviously result in a poor performance. So underfitting, you can just look into the data and say like, obviously it will lead into underfitting, because you have very, very less data and training and thing is highly not possible, and it will result in what is called actually like an underfitting thing, meaning like this. So when you actually train the model and leave it, what will happen in any of the test data input that you give, you will never fit in any of this line. Everything will be falling outside the line. One is that will be fitting exactly on the line, 100%. That is overfitting, because it has learned too much from the data, including the dirtiness. The other one is something, the data is too less. The overfitting, the data is huge, no doubt. You might have in 1 lakh data sets, but there are too much of dirtiness, actually missing data and things that has not been handled properly, resulting in overfitting. Underfitting is the data set we have is just like 100 or 200, that's all. So with that, you want to actually train it. When you train it, what will happen ultimately when you actually plot it? The test data will actually fall outside the line which you have built. That is the model you have built it. A good fit is like this, wherein you can see there are some models that are fitting within the line, some model falling. So that is actually called as a good fit, where the data balancing, the data cleaning, everything has been done up properly actually. Okay, so this is a very, very important thing that you always look into the data set before we actually proceeding to the measure. That's why initially stage we do what is called data exploration thing in order to find out whether the data is well balanced. So the problem of actually overfitting or underfitting doesn't come. And also we look into the missing data and try to handle the missing data by doing things like mean or median, or sometimes we replace it with zero values. If we have a large data set, there are some missing values. Sometimes you can actually delete it. Sometimes you can actually replace it with the mean or median values, or replace it with the zero actually. So it depends on how large the data sets are. Now, in connection with the underfitting and overfitting, there is something called a bias and a variance actually. So if the model is actually going to be overfitting, meaning it is actually fitting the test data very perfectly on the model you have built, it will always have what is called a large bias. So if the bias error that you compute, which is computed based on what is called your actual value and the predicted value, when you calculate, you'll find an error. If the error that you're getting is a too large a bias, then you can come to a conclusion that yes, it is actually an overfitting model actually. Variance is something like it is predominantly done for underfitting, it actually comes. So if it's an underfitting thing, wherein the data you have is an underfitting thing and you have plotted the model and thing, so most of the data actually falling in the outliers, it is not fitting into the line, that is called underfitting. So in that case, we actually compute the variance again between the what is called the expected values and the predicted values. So you take what is called like x square minus e of x the whole square, you compute the variance. So when the variance is calculated, we have a very high variance, then you can say the model is overfitting. So that's why we calculate in the machine learning before we start data exploration, try to compute the bias and the variance. So from the predicted and the expected values, we actually try to see how the bias and the variance is. If it is too large a bias or too large a variance, so we come to a conclusion that it is either an overfitting model or an underfitting model because based on the data. So there should always be a trade-off between the bias and the variance, which actually tells you how the bias and variance should be. It should be too low, it cannot be too high, or if the variance should be too low and it cannot be too high also. So there's actually a midpoint actually called the optimal level where you have to have, wherein the bias and the variance actually has a trade-off. Always there will be a bias, there will be a variance error, no doubt about it. But that bias and variance should be such that it is well balanced and the model behaves properly without leading to overfitting and underfitting a problem actually. Now, so now that you have learned how to handle the overfitting and underfitting, wherein the data handling is a very, very important step before applying the ML model and thing. When you start applying the ML model, there are certain things called hyperparameter tuning. Why you do hyperparameter tuning is in order to achieve a very high accuracy. Let's say your data has been pre-processed properly, you've handled everything, there is a good trade-off between bias and variance, the data is well distributed, all the dirtiness and things in the data are removed. Now we'll have to look into, while you're applying the ML algorithm, how you're going to work with the hyperparameter. What is a parameter and a hyperparameter? See, parameters are the inputs that you get from the data. For example, I have a data set of a medical wherein I have the inputs, say the age of a person, his medical conditions, and those, they are parameters. Hyperparameters are something which are specific to the model. So you try to fine tune that hyperparameter of the model in order to achieve the best accuracy you want actually. So that is called as a hyperparameter. And the process of searching the best hyperparameter in order to result in what is called an ideal or an optimized model is called as hyperparameter tuning. So some of the example is like we're going to see forthcoming about the various ML models. What the linear regression, whether polynomial features should be used or least square should be used. What is the maximum depth in the decision tree? When you talk about neural, number of neurons that has to be there within the hidden layers and things. So these are the things, or the learning rate. So these are the hyperparameters that you try to actually fine tune it in order to have the best optimum model with a good accuracy actually. So in hyperparameter, there are two ways actually they tune it. One is a grid search and a random search issue. In grid search, what they do is rather than fine tuning each and every parameter and doing it, what they actually do is they actually make a matrix wherein they actually collect a collection of hyperparameters for the model. So they might have multiple hyperparameters model. So those models alone, those hyperparameters actually you take it and you actually form it as an array. So you actually use it as a combination. It actually has a combination of X, Y, Z are three hyperparameters. You have one combination like this. You have another combination. You have another combination. And in that, you try to see which one gives you the best optimized model, and we just go with it. So that is what is done as in a grid search, wherein like simply build a model with a combination of different hyperparameters. So that's what is a grid search actually. So you actually go as a combination actually. A combination of this, a combination of this, a combination of this. So in that you actually select the best one and try to optimize the model. Then is random search. Random search is very different from the grid search, wherein they actually use a discrete set of values. So they don't use a combination of hyperparameters or anything. They actually follow some statistical distribution, wherein the values are taken randomly and accordingly they are sampled. to get the best optimized model. So as I said, in machine learning, you actually split the data. One way is splitting is you take a combination of 70-30, meaning 70% you have to take for training and 30% for testing, or 80-20. Some go for 90-10 also these days, but I prefer like 80-20 only. 80% for training and 20% for testing. Sorry, it's an error there, not 205, it's 20%. Sorry about it. Now, when you're saying 80%, let's say you're going to work with 100 data sets alone. Think about when you're going to take 80% for the training, then what will be there for you for doing the testing, right? That's the reason why we have to always go for a larger data set, wherein the problem of underfitting or overfitting problem, particularly underfitting, does not happen. The other method is they use something called k-fold cross-fold. Rather than going 70-30 or 80-20, they actually make a fold of n folds of the data or k folds of the data. The k can go maximum up to say 10 action. So when you take k folds of data, you take a combination of the data action. Okay. So in that, when we have, let's say here they have taken k as 5 folds of the data. In that, what they will do is like the green ones here, these folds actually they use it for training, and the fold one you use it for testing. In the next iteration, you change it. You make fold 2 for testing and the remaining folds for training. Then similarly for the third iteration, fourth iteration, fifth. So this way, they actually try to see which of the fold of data which I've used for training and testing gives me the best accuracy. Okay, so that's called a k-fold cross validation. So now, having seen how data cleaning has to be done to avoid overfitting and underfitting, and the bias and the variance, and obviously looking into the hyperparameter tuning, and then into what is called the k-fold cross validation thing. How are you going to validate the model? How do you know which of the model is the best model for my data set that I'm getting the prediction? The one thing that we talk about is what is called as a confusion matrix. What a confusion matrix says is, when the word it can say it's a confusion, I mean it's a confused matrix. No, it's not. It's a name given. It's actually a performance of a classification model, which actually says which of the ones are good ones, which are the ones are the bad ones. Meaning how many true positives you have, how many true negatives you have. Meaning positive recognized as positive, negatives recognized as negative. This is the correct one. The bad ones are positive, it is a false positive, meaning it is a wrong value, but it is actually telling it is a positive value. Then a false negative, it is not a negative, but it's saying it's a negative. So how many of those samples are there? That is the confusion method. Now based on that, you actually compute certain errors like precision and recall, which actually says how many number of positive results are there divided by what is called the number of positive results. That is the correct positive, that is true positive, by the total number of positive, that is true positive, the false positive. The recall is something like the number of correct positive results divided by the number of all the relevant samples. So this precision and recall will actually say, if we say that you have a precision of say 80% or recall is 80%, that means 80% of the value has been predicted properly. Only like 10-20% is actually been predicted wrong. Based on that, only the accuracy is decided. Let's say you have a precision recall value. It's a curve actually when you put it is falling below 50%. Let us say you're getting a 40%. That means 40% only has been predicted properly. Remaining 60% is predicted wrong. So that will result in a very, very low accuracy. That means your model has not been trained properly, and obviously your data has not been handled properly. There is some problem or issue, either it is overfitting data or underfitting data, some kind of an issue where the prediction has been wrong. Even the data could be fitting properly, but all the predictions are wrong. It is giving a very low precision recall. That is the indication. Then F1 score, which is dependent on the precision recall, which should lie between 0 and 1 actually. Then is the accuracy. And accuracy you actually compute for both training and testing, because during the training we have to see how much of accuracy you are achieving, and during the testing also we see the accuracy. So when you compare the accuracy during the training is 90 and the accuracy during testing is 60. That means there's a large variation. So your model has not been built properly actually. Okay, so the accuracy between the training and testing, there should not be much variation. A variation of plus or minus 5% is acceptable to some extent actually. Okay, so that is about the accuracy. So some of the machine learning algorithm which I'm going to actually discuss, not very much in detail, but a little bit brief actually, I can say, or supervised one. Unsupervised, I'm not going to touch it actually. Okay, so supervised one I know. So the first classification is what is called a regression. A regression meaning it's going to follow the standard line equation. The one of the most standard one we use is the linear regression. Then we have even polynomial regression also. And then under the classification category, we have things like naive Bayes, support vector machine, also called SVM, then logistic regression, then trees like decision tree and random forest and k-nearest neighbor. Then you have other variations like ensemble learning and things like that. Lots actually we can say. Linear regression. Now, when do you apply linear? So one of the major questions, mostly when students come to do a machine learning project, I normally ask is, have you collected the data set? The next thing is, what is the kind of a model you're going to apply? Because today, most of these algorithms, actually, you're not going to sit and write. Everything is given as libraries inside the Python or MATLAB. Okay, but you need to first understand, as I said, how to handle the data, how to actually avoid the overfitting and underfitting problem, whether the data is well balanced by doing expression. These are things, rudimentary things that you'll have to manage. Only then your machine learning can be applied and you can get the best accuracy model actually. Right? Then the next thing I normally ask is the hyperparameters in the model. Then the fifth thing I'll say is, what is the kind of a model you're applying for this data set? That is something that makes the person to actually think, what kind of model I should apply? So you need to understand which model is suited for what. Whether you can apply this logistic regression for this data set or can I apply linear regression. You have to understand whether this model can go with this data set or not. So linear regression is predominantly applied for things which are having continuous values. Continuous values meaning things like sales forecasting. I want to forecast the sales of a car, or I want to actually forecast about the rainfall, or I want to forecast like how much amount of water I need for the next 24 hours or 48 hours. So those are problems where you actually plot the curve between what is called the independent and the dependency data. That is sales versus the years. I want to forecast. Linear regression is a very good starting point actually for such kinds of data. Such kind of forecasting problem that we are actually going to see in the case study how linear regressions are used for those kind of a problem. So that is actually a very good starting point actually, which is actually based on a standard line equation y equal to mx plus c, where m is the slope, x is what is called as the dependency variable, and b is the intercept. So you calculate the slope and the intercept and just plot the line. Same thing, you're going to take an 80% of the data, try to compute that equation and try to plot the line. So you get what is called a regression line. Then when you give the test data should fit the regression line in such a way that there will be some outliers and things. And then with the test data you give, when a regression line is given, you actually try to compute something called R2. R2 is actually to understand whether the line that we have actually plotted based on the data points is actually fitting the model properly or not. So that R2 will actually give a value between the range of 0 to 1. 0 meaning the points, it is not a good fit. 1 means it's two best fit actually. That's also good. So it should be in the range of 0 to 1. That will say whether the points are fitting the model properly. So problems related to things like continuous variables, like forecasting and things, linear regression is a very good starting point actually. Then is logistic regression. So people always think when we say logistic regression, where it can be used for regression. For example, again, like linear regression, but that's not. Logistic regression, as the word says, it falls in the category of classification. Now, in this one, the data sets you are actually having are something like they are not continuous values, they are all discrete values. Discrete values meaning, let's take an example here because with an example it will be easier to understand. I'm having a data set which is actually saying like the name of the person, or let's say there's no name, like age of the patient, his medical diagnosis, and I'm having an output value which says whether the person is having COVID or not. But that is the current situation. Let's take COVID. That's the easiest way to understand it. So let's say like whether it's having breathing trouble, whether it's having fever, whether it's having cold, whether it's having any kind of loose motion, all the features. Let's say whether it's having COVID or not. 0 and 1. The true condition. Yes or no. That is called discrete error. So in such kind of problem, logistic regression is what you're going to, because you're going to classify whether the patient is having corona or not. That is what you're going to actually classify it. Right. So what we actually do is, based on the data sets we have, we try to compute the probability of the occurrence. That is the probability of the occurrence of corona or not, because these are all supervised learning. So you need an output label. The output label is already given. So based on the various features, that is the values of X and thing, we actually try to compute the probability. That will say the probability of the occurrence. There is probability of occurrence 0, there will be one value. 1, there will be one value. You might think whether it will be same value repeating. No. Based on the different features you have, it is actually going to compute the probability of that occurrence. That is occurrence, whether yes or no, you'll have the probability value. So based on those features of X, you will actually plot the probability curve, which actually follows an equation 1 by 1 plus e to the power of minus x. So this probability curve actually ranges between 0 to 1. So for a probability value below 0.5, okay, it actually has an output 0. The probability value above 0.5 to 1, the output is actually 1. So that is where logistic regression is used. So anywhere where the classification is actually binary, you can go for logistic regression. You also have multinomial regression, where you can be used for multinomial presentation. That is multiple value presentation also. A similar probability values can be computed, and accordingly you can actually use it also. Okay. Then comes as what is called a support vector machine, SVM. Support vector machine is actually used for classification, which actually develops a non-probabilistic classification, meaning it does not go on the principle of probabilities. It does not compute probabilities of occurrence like what we saw in regression. So this actually, again, the same corona problem will take. Same diagnosis and same symptoms. I'm actually going to classify whether the person has COVID or not. So what I will do is, I will just plot the points about the symptoms of the patients and thing against, let's say, age or something like that, and that will be plotted. So when I plot it, actually, there will be some points which will be lying on the on one side of the plane, which is like corona patient, and some points which will be lying on the other side of the plane, which is non-corona patient. Based on the symptoms and thing, obviously you have to convert certain things as numerical and thing. Obviously, you'll have to do that and accordingly plot. So there will be one spatial line that is actually would divide the thing into the two different classes. That is class A and class B. So based on the plotting, a support vector machine, a hyperplane is what will be generated. Okay, that will demarcate good data and a bad data, or a corona and a non-corona patient. Something like this one. A hyperplane will actually be, that's when support vector machine, when students do, we say whether a hyperplane has been generated. So only then we can actually classify the data into whether it falls into category A or category B. But this method can only be applied only for a binary classifier. Anything which actually goes beyond that, if we have multi-level classifier, SVM is not a good fit actually. You have to go only for other models, or even like logistic regression can actually be applied for multi-level classification. You have something called multinomial regression, where you compute probability for different outputs of the occurrence. Rather than 0 and 1, you will have actually like, for one occurrence, you can have like same 0 or 1 with different probability values. And obviously you will have multi-level classification. Logistic regression can actually be used. So you'll have different such kinds of probability curve that will be plotted for different outputs actually. Okay. So that's what is SVM is about actually. The hyperplane is the one that decides to classify the data from two different classes actually. Then is what is called as a naive Bayes. Now naive Bayes is actually a probabilistic classifier again, but this can be used for larger data set. Also, it computes what is called a probability, but the probability that it will compute is not based on the occurrence or anything. It actually creates what is called a likelihood table. Okay, a likelihood table will actually be created as. So it follows a method called a Bayesian method. The lots of Bayesian method, one is naive, there's something called Gaussian, lots of different, but naive Bayes is the most traditional method that we use in the machine learning. So let's take a very simple example, which is like a data set, which is actually going to consist of a thing about whether about like playing cricket. So for us to go and play cricket, what are the things that we have to see? Forget about the gadgets and things, about the environmental condition. Let us see the weather. So weather, there are three things. Let us say, is it raining? Is it sunny? Is it cloudy? The three things actually. Okay. So for each of the three things, there will be a value 0 and 1. Yes or no condition. So based on that, we'll have an output whether you can play cricket or not. So the condition here would be you can play cricket only if it is sunny or even it is cloudy, but not rainy. So if it is rainy, obviously you can't play the cricket. So we compute what is called a conditional probability, which is given here, PA of P, which says that probability of a conditional probability A, which here means like playing cricket, yes or no, over B. B meaning that assuming that the events probability is known, the events probability here is like probability it will rain, probability it will be sunny, probability it is cloud. Those things are actually known for the condition that you can play cricket. Okay. Similarly, you actually compute for a probability that you cannot play cricket. Again, the events actually you know, which is actually like rainy, sunny, and cloudy. Then you find a probability of sunny, rainy, and cloudy, yes or no. Based on that, then you know the events probability, this probability of failure, this probability of playing cricket or not, into the probability of B, the probability of B. So what exactly you do here is you actually take what is called the data set, you compute what is called the likelihood table. So the likelihood table will be calculated like for playing cricket based on one particular parameter, let us say sunny. Is it sunny or not? And how whether you can play cricket or not. For that, you compute the likelihood table. You will see the number of such occurrences, compute the probability values and things. Then similarly, you take for rainy, playing cricket or not playing cricket. Then cloudy, playing cricket or not playing cricket. So based on those probability values computed, you try to compute probability of playing cricket equal to yes for the condition where rainy equal to no, sunny equal to yes, cloudy equal to yes according to calculation. Probability of not playing cricket where sunny equal to no, rainy equal to yes, and cloudy equal to yes. Or no, actually you can take and you compute the values. So based on those probability values, you make a classification. What is the probability that you can play cricket or not? So based on those probability values and things, you make a classification section. Okay. So that's exactly how a naive Bayes actually. It doesn't go by any kind of a thing like plotting like how we saw in logistic regression. Based on the probability of occurrence, we actually set the values as 0 and 1 according to it, or like SVM by plotting a plane. It goes completely based on naive Bayesian theorem, where actually it tells the probability, that is the likelihood table, the probability of the occurrence. So the likelihood that whether you can play cricket or not, based on certain things are computed. For that, you compute what is called the likelihood of the frequency table, where probabilities are calculated. Accordingly, you make a computation and do that classification. Then you have what is called the K nearest neighbor. K nearest neighbor is very simplest one actually. You can say something like a logistic and thing. Again, a very simple thing that they actually go by what is called a majority rule. It's a non-parametric method actually used, but this actually can be used for both classification as well as regression. It can be done for both. So what they actually do is you have a data set, say X and Y. Okay, we actually calculate the distance between the training data, testing data and the training data. For calculating the distance, we actually use what is called Euclidean distance. There are many other distance mechanisms also. For example, Manhattan distance is there and things, but Euclid is the most predominantly used thing in K. So Euclidean distance is a very simple thing where what happens is when you have x1, y1, x2, y2, you actually use the formula root of x2 minus x1 the whole square plus y2 minus y1 the whole square under root. That one you calculate. So you calculate for that particular test data with all the training data the values. So once you've calculated, Now there is something called the value k here. K equal to what? So normally if k equal to 1, so you will allocate the test data to the minimal position, the one nearest. So normally we go up to say k equal to 2, k equal to 3, maximum is k equal to 9 or 10 actually we go. So most probably people actually choose k equal to 3. So it is actually done only by iteration actually to find the one which is closest. So based on the distance value you calculated, if k is set to 3, in that will actually rank. Ranking is based on the distance which is having the least value. The one which is having the least value will be given the rank 1. The next least value will be given the rank 2. And the next least value will be given the rank 3. And based on that, actually, you make the classification whether they fall into class 1 or class 2. So that is what it is. So if you look at here, you can see k equal to 1, k equal to 3. So based on that, we can actually say whether the particular training data falls under which class or not. So that is so. So you can see like this one is very close to, new example is very close to this value, k equal to 1, then it's a k equal to 3. Accordingly, you make that calculation. So this is a very, very simple thing actually, followed by the what is called the Euclidean distance. The next thing we are going to talk about is tree-based algorithm. This actually falls again under the category of both classification and regression. They actually call this as CART. Is the model they say. CART meaning it's actually for classification and regression. CART is what they say. Sometimes if you Google, you say like CART model, this is nothing very new. It's actually a model which actually falls in both the categories. Now what the decision tree does is it's actually used for both categorical and numerical data. Categorical meaning categories, like having corona or not, having heart disease or not, categories and things, you can actually use this one. So what this one does is, it actually follows like from a big large data sets, particularly when you want to diagnose a person for like a COVID or heart disease, you actually look for certain symptoms. You say, what is the age group? Is the age more than 50 or less than 50? If it is less than 50, then look whether he has fever. If he has fever, then look whether he has a breathing problem or not. All these things you do. So these things you actually build it as a decision nodes. And each of the decision nodes are actually going to be traversed down actually to get the last and final decision, which are denoted by the leaf node, whether the person is having COVID or not. So that is what is actually done in a decision tree. So like this one. So like this, you actually build the decision tree, where you actually see how much is the depth of the tree and things like that. The entropy is calculated. Accordingly, the decision tree is actually built. Random forest is nothing but an extension of decision tree. So when do you go for a random tree? The data set you have is very, very huge. So the number of decision nodes you are going to have is very large. In that case, you predominantly go for random forest. It's nothing but collection of multiple decision trees. So in this, what they actually do is they construct multiple decision trees, and the decisions coming from each of the decision trees are actually taken. In that, they say that which one is having the maximum vote, and that one will be the final class actually, they say. Okay, I think I'll stop here for now. I give a short break, about say 10-15 minutes, and then I start with neural network.